I think there's a couple of people coming in, but yes. So welcome back, everyone. This week we are delighted to be joined by Veronika, who has just joined the EBD as a Ramón y Cajal researcher. She's actually been in Sevilla for quite some time already, but working primarily at UPO, and she'll explain her kind of trajectory a little bit. Initiated her career on freshwater ecology, but has kind of moved into more of a kind of environmental epidemiology and sort of a focus on human health. So very excited to hear Veronika speak. The floor is yours. Thank you for speaking.
Yeah, thank you, John, for the nice introduction. And yeah, great to be here and to be able to talk a bit about my work. As John said, I just joined EBD a month ago. And I didn't have any prior collaboration with EBD, so I also thought it's great. This is a great opportunity to tell you a bit of what I do and maybe to see where we can start collaborations, and let's see. So I will talk about climate and health, and I will talk a bit about my really deep past of phytoplankton bloom or freshwater ecology research, and then I will talk about temperature-related mortality and human heat stress. So, but before we dive into my research, I thought, okay, I show you a bit of what is my background. And actually, 2 weeks ago, I was listening to the seminar, and I saw all of these migration patterns of birds. So I thought that, okay, I show you my own personal migration patterns. And so, yeah, I actually, as I said, so I did my PhD at a research institution in Berlin on climate impact of freshwater phytoplankton blooms. And then I actually also worked a really long time at the Potsdam Institute for Climate Impact Research, and there really also kind of, had a few years outside of real academic research, but I was involved in scientific policy advice on climate change, and I was also involved in a huge model intercomparison project on climate impact models on a global scale. And then I actually moved to Sevilla, and I had different affiliations, and I was with the Marie Curie Fellowship in Munich, and within all of this time in Munich and Sevilla, I started working on climate change and human health. And this will be also the focus of my talk. Okay, so this is the outline, something on phytoplankton blooms, and then I will give you some also introduction motivation of why I work, and I think it's very interesting to work on climate change and health and temperature-related mortality. Then something on the methods, because I thought maybe these methods that we use in environmental epidemiology, they are also applicable to ecology, so it could be also interesting for you. And then, so then I will show 3 key research questions that my collaborators, myself, we have approached in the last, I'd say, 10 years, and then some outlook on future research. So let's start with some lake. So this is a lake close to Berlin, and that I worked on. It's a shallow lake. It's a polymictic lake. And the nice thing about it is it has a long-term monitoring program and with very, very long time series on physical variables. And this is what I worked on. And this is actually something that I still do. I still work with time series analysis. Now I work with human health indicators, but it's something that I have kept doing. Okay, so I just thought it's nice to show you 2 studies that I did at the time. For you to understand a bit the type of research that I've been doing. And so in this very old study already, what we were actually interested in were the phenology of the phytoplankton bloom. So as you know, with climate change, the phenology of many systems is changing. So I don't know, trees are blossoming earlier, but also in these lakes, the phytoplankton bloom appears earlier in the season. And here what you can see, it's the deviation of this diatom spring peak across this time series, and you see that there's a forward shift in this bloom timing, which is actually quite correlated in the system with the timing of the ice off. So when the ice gets off of the lake, the light penetrates into the water and the phytobloom starts growing. But what you actually also see here is that there is this trend towards earlier ice out. And here, actually, you had years without any ice. And then if you look a bit more closely on the time series, you see that here there were very, very early spring blooms. And a bit later in this time series, despite very early ice out, the bloom occurred later. So that was one question that we were asking at the time. And actually, the hypothesis was that this was actually had to do with another big environmental trend that happened to the lake, which was the decrease in the phosphorus input to the system, which you can see on the right side. And where you can see, here the total phosphorus concentration during the spring. And you can also see the biovolume of total phytoplankton and diatom during the spring peak. And so the question was really whether this kind of belated spring bloom, despite very warm conditions, was actually due to this trend in decreasing phosphorus. And what we did at the time, we built a process-based model for this dynamics of the phytoplankton spring bloom. And I will just show you now the output from this model for 2 years, which were similarly warm, had similarly early ice out, but the spring bloom appeared much later in this year than in this year. Okay, so this is now the results for these 2 years. And you can see in the symbols are the observed diatoms and the grazer biovolumes. Daphne, which is the main grazer of the phytoplankton. And you can see now these 2 years, one in the phase of very high phosphorus concentration, and the other one in the phase of lower phosphorus concentration. And you can see then in the lines, this is the output of the model. You see it quite well. And what we actually realized then was that the collapse mechanism of this bloom switched from a bottom-up driven mechanism to a top-down driven mechanism, where in the phase of the highest phosphorus concentration it was actually a secondary nutrient silicate that limited the phytoplankton bloom so that it collapsed. And then in the period of lower phosphorus concentration, the bloom actually collapsed because of the grazers appearing. So in a way, we showed in this study that really with these two big environmental drivers, warming and changes in the phosphorus input, how these interacted and how also the response of this system to climate change was dependent on this other environmental trend. Okay, so one more thing about phytoplankton bloom, and then we will drive into my main research focus now. So then another study that I thought I would show you is this one, where we looked at cyanobacteria blooms in the summer. And actually there was the observation in the lake that with 2 similarly warm heat waves, in 1 year there was a strong cyanobacteria bloom, in the other one there was none. So this you can see here. So these are these 2 years, so 2003, 2006, they had very strong warming. So you can see here the interannual variability in water surface temperature, and you can see that both of these years had similarly warm summer temperatures. And then, but you can also see here that actually in the 1 year, 2006, there was a strong cyanobacterial bloom developing, and the other 1 year there was hardly any or much less cyanobacterial bloom. So the question was really why, if the temperature was similarly high, and we know that these phytoplankton blooms are favored by these warm temperatures, why did it happen? And I won't go in much detail here, but we actually, with some classification tree analysis, we could identify some critical threshold of stratification intensity of the lake that actually explained these differences. Okay, and so now we move to human health. And it's really, for me, difficult to talk about this because this is a very long time ago, but I hope I could at least transmit a bit of what I did at the time. And so, yeah, of course, cyanobacterial blooms, they have some public health implication. As you know, with a cyanobacterial bloom, they have, if you go bathing, for children, for other people, for people who are deprived immunologically, it's dangerous. So if these blooms appear, many of the lakes and rivers are closed for bathing. So this is my first touching with the health field, but let's now move to what I do now. And so how did I get motivated to move actually from ecology into this field? And actually one of the motivation was this. So at the time when I was involved in the scientific policy advice on climate change, I also got, I often was confronted with these claims of climate skeptics. So in this case, people who think, okay, with climate change, it's all not that bad, it might be even beneficial. So there is this claim that actually with climate change, because you would expect that there's an increase in heat-related mortality, but you would also expect a decrease in cold-related mortality. And there's this claim that actually the decrease in the cold-related mortality will outweigh the increase in the heat-related mortality. So overall, that you could expect that global warming will actually be beneficial, and you would see decreases in overall temperature-related mortality. So, and I was really wondering, might this be true? And so maybe another motivation is that I have been living in Sevilla and experiencing the heat. So that's maybe another reason I switched these research fields. So now let's look at mortality data. So this is now mortality data from Sevilla. And what you just see here is daily death count. So all deaths that occur each day in the city. And what I did here now is I just fitted some spline functions so that you can see how this mortality changes over the season. And what you actually see, and this is very typical for all of the temperate climates that you see, that you have, is that actually mortality in winter is higher than in the summer. So there is this seasonal driven mortality pattern, which already hints something that there might be it might have something to do with temperature as well. Okay, let's look another way at the Sevilla mortality data. That's another data I have on my computer, and I just plotted this way. So here now you have, again, the season, and I just took out the years for 2003, which was strong heat wave, which is in red, and then I just plotted also the median of the previous 5 years in black, and you can see also the range. And you can see that when this heat wave took place, you can really see the strong excess mortality, this signal in the mortality. Okay. Just something maybe to maybe strengthen why it's so important to work on this topic. As you know, 2003 was this extreme first kind of heat wave in Europe. There were 70,000 excess deaths due to heat in Europe, and Paris was very strongly hit. They needed to put up a phone line for relatives to search for victims of the heat wave. There were so many people dying. And here's, for example, a comparison of this 2003 mortality spike in France, and you compare this to the first wave of the COVID. This is now for all of France. It's the same type of graph that I showed you before for Sevilla. So you can see here how during this heat wave mortality strongly increased. And you can see that even in the peak, the highest number of deaths per day were higher than the highest number of deaths in the COVID wave. And of course, it's the integral of the curve that matters, because it's the total number of people dying, but it's still very, I think, impressive to see that heat can have such a strong effect on mortality. Okay, and then of course 2003 is 20 years ago. Let's also look at something more recent, and this is just a paper coming out last year where it looked at the 2022 summer, which was actually the hottest summer on record since, in Europe. And there was actually also estimates that around 60,000 people died due to heat. And you can see here that especially Southern European countries are strongly affected, and were strongly affected by this event. Okay, so this is why I study this and why I think it's very important and interesting to study this. Okay, now let's move into methods. So all of this work is based on data, and what we usually use is these time series regression models. And maybe the most kind of exciting thing is that there's like this approach which is called the distributed nonlinear models, which I explain a bit further, where you actually really account for the nonlinear effect between temperature and mortality, and you also account for the lag effects between temperature and mortality. Yeah, and of course, I guess in all of these regression models, you control for confounding baselines, and you can try to confound for, try to control for the confounders. Okay, and so then what then comes out of these type of models is these type of relationships where you have the daily mean temperature here on the x-axis and the relative risk of dying on the y-axis. And here you see in the histogram, this is just the distribution of the daily mean temperature across the study period. And what you actually see that there is this, what we call the minimum mortality temperature. So there is kind of a optimum temperature where this relative risk is lowest. And then above this temperature and below this temperature, this relative risk increases. And for example, a relative risk of 2 at kind of 30 degrees daily mean temperature in Berlin would mean that you have a double likelihood of dying due to temperature than at this temperature of around 20 degrees here. Okay, so but then, yeah, one important thing, and this is what brings me back to these distributed lag nonlinear models, is that actually this, what I show here, is the cumulative risk across all lags. So in this case, for example, we looked at 3 weeks of lags, so 21 days of lags. Because behind this is actually this structure. This is so where you have here the temperature, and here you have the lags, and you have then here these risk landscape. And of course, you can also now look at how these lags, how the lag pattern looks like. And for example, if you imagine you take a slice at -5 degrees here, and then you get this curve, or you take a slice at 25 degrees and you would get this curve. And what it actually suggests is that for cold, the risk rises, is highest, and it stays actually high for almost 3 weeks, while for heat, it's very an acute effect. So you would have, on the same day of the high temperature, you have a strong relative risk, and then it drops very quickly. And you also get actually these very interesting phenomena, which is called the short-term harvesting, which you can understand as you have a pool of people, older people who are susceptible to die, and then a heat wave hit, and so these people die, but then a few days later, less people die because the pool of susceptible individuals has been reduced. Okay, and then one more thing about definitions is now when we talk about cold and heat-related mortality, we just use this reference temperature, so this minimum mortality temperature, and any temperature below this is cold, and any temperature above this is heat. But what is important to take in mind is that here, for example, what they also looked, they had 2 other thresholds, so at the 25th and the 79.5th percentile. So if you also do this, so you define moderate cold, moderate heat, and extreme heat. And then you attribute mortality to this. What is shown here is the attributable fraction, so percentage of mortality in the year that can be attributed to these cold and warm temperatures. And you can actually see that most of it can be attributed to the moderate cold. So that's something important to take in mind when we talk and we compare cold-related to heat-related mortality. But for you now, important to understand is just anything below this temperature is cold and anything above is heat. Okay, so one more thing, what I showed you before now is just total death count. So I didn't talk about the causes of death. And maybe just one comment about this is that if you actually look at causes of death, you find that many, many different causes of death show this association with heat. So, and most of them actually are respiratory and cardiovascular causes. But sometimes people think that when we talk about heat-related mortality, it's these people who die from heat strokes. So agricultural workers that get a heat stroke and die. But no, this is really out of these statistical associations. Most people, most causes underlying what we find are actually respiratory and cardiovascular causes. Okay, and then one more thing about kind of the type of approaches we take. Yeah, there have been a strong movement in environmental epidemiology to really pool data. And I have been involved now for a couple of years in this multi-country, multi-city collaborator. And we actually contribute German data to this network. And by now, we actually have data on 54 countries in quite nicely overlapping periods. And so some of the work that I will show you now will be based on this huge data set of that many mortality statistics. And maybe one more thing also maybe interesting for you working on ecological systems is that because we have these huge spatially resolved data sets, what we usually do is we take this two-stage research design. So you imagine you estimate your associations between temperature and mortality for each city. But then, of course, you're also interested in pooling them. And so then we use kind of these meta-regression approaches to pool this. And I will illustrate this with a few examples of my own research. So, for example, here, for a study we did on 12 German cities, you would estimate your temperature mortality association for each city. And then the model coefficients you pool actually and then in these linear mixed effect models. And you also use some meta predictors. So maybe in this case, we used some mean temperature and temperature range which reflect kind of the climate of each city. And what you can then do, for example, is out of these meta-regression models, you can derive improved estimates of your association in each city. So that's one thing which is nice. And another thing which you can also do with this type of approach is association. So you would have, again, your 13 cities here. And in this case, actually, we didn't only look at these 13 cities, but we also looked at different time periods, trying to understand what happens over time. And so then you pool again your associations. And for example, in this case, which is interesting and you find in many, many cities and regions around the world, if you here look again at temperature and relative risk, and this is the heat-related mortality risk, and you look at it across different periods, you often find this pattern that there's actually a decrease in the vulnerability. So at the temperature that used to have a very high risk of dying, more recently, there's less vulnerability and there's a lower risk for the same temperature. Okay, and another nice thing you can do, of course, once you have these meta-regressions, you can also pick out certain meta-predictors, so certain, possibly explanatory factors. And this is something, for example, we also did in this study where we had this result of decreasing vulnerability over time. And actually, if you look at, for example, at the predictor of life expectancy, we found that actually with higher life expectancy, this suggests that this increase in the life expectancy is behind this decrease in the vulnerability we are seeing in these German studies. Okay. Okay, now I picked out 3 research questions, and now out of the many things that I have been involved with, that I thought that are maybe the most, relevant. Let's see. Okay, so my first research question, which has to do with future prediction under climate change, is this one. Will decreases in cold-related mortality overcompensate for increases in heat-related mortality under future climate change? So we come back to this climate skeptics idea in the beginning. And so this is just one study we did for Germany, where we projected cold and heat-related mortality under different climate change scenarios. And actually, in this case, we looked at different levels of global mean temperature rise. So 1, 2, 3, 4, etc. Global mean temperature rise above pre-industrial. But what is now interesting is this question: is cold-related mortality decreasing more than heat-related mortality will increase? And what this study suggested is this is the result for all of the cities, and these are the different cities. And actually is that, there might be nothing much happening until maybe 2 degrees of global warming. But if you go to higher degrees of global warming, this study suggests that we should expect actually a net increase in the temperature-related mortality. Maybe for some cooler cities, this is not the case, but overall, you would expect that there's actually a net increase in the mortality. And then I was also involved in a similar study now looking at very many regions of the world and pretty much asking the same question. And in this case, again, you see changes in heat-related and cold-related mortality in the net change. And in this case, it's just shown for, I think you cannot see it well, but it's just shown here for different climate change scenarios and for different decades up to 2100. And what you find overall, that in most regions, actually, you find the same pattern that we found for Germany, that actually we need to expect a net increase in the temperature-related mortality, but there is also some exceptions. There's the Northern Europe, for example, East Asia, where even for the highest scenarios, for the strongest warming, you would then, according to this study, expect a decrease in the temperature-related mortality. But what is important is that we actually find these strong increases in the most populated and poorest countries with least adaptive capacity. Okay, and one more thing about this. So overall, we have this clear evidence that this climate skeptics claim is to at least not generalizable. But what I wanted to show you is some very, very recent work because what I showed you before, you neglect adaptation and you also neglect any changes in demography. So there's no changes in the age structure of the population that you account for. And we know that actually older people are more susceptible to heat and to cold. You can see this here. So you have here for 4 different ages, you see these same curves. So temperature on the x-axis and the relative risk. And you can clearly see that here this pink. So 85% population has higher relative risk than the youngest age group, and this is especially pronounced for the cold, for the lowest temperatures. And now you could do the same type of prediction, but you account for these, you account for changes in the demography, so you account for population aging. And then again, you look at, so will climate change lead to an increase or decrease in total temperature-related mortality? And this is just one map showing the city-level net changes in these excess mortality rates at 3 degrees of global warming. And here, and the green would be a decrease in total mortality, and the pink would be an increase. And you find again that John is happy because in the UK is doing well. But you find that in most cities, especially in Southern Europe, you would actually expect a strong net increase in temperature-related mortality. And you can pick out Sevilla, which is here, so Okay, so that was this one research question. Now let's move to another key research question that I tried helping to respond to. And this is on the topic of attribution. And so here the question is, has climate change already induced an increase in heat-related excess mortality in the recent past? So we are no longer looking into the future, but we are asking, so how are we by climate change that has happened in recent decades? Okay, and so again, this is one of these multi-location studies. This is just showing the number of locations that we included in this study. 43 countries. And then the way this was done now is that you take data from global climate models, and these models, what they usually produce, they have like these simulations that take into account all of the human forcings, so greenhouse gases, aerosols, land use changes, etc. But they also have these simulations that only take into account natural factors. So where the simulations are only driven by changes in the sun or volcanics, so which is this, in this case, it's this orange line, which is the historical naturalized forced runs. And this darker red line is the with climate change. And of course, you can then just take these global climate model simulations and take out the data for all of your 700 cities. And this is what has been done here. And this is just the average across all of the cities. And this shows the annual average temperature across the 20 centuries up to now. And in this study, we actually looked at the period 1991 to 2018. And used, and here you can actually then now see for all of the countries, you can see the the temperature increase attributable to climate change. So it's just the difference between this curve and this curve for all of the different cities and all of the different countries. So you would have between 0.5 degree and a bit more than a degree attributable to climate change of the warming that these cities experienced. Okay, and then with this, of course, you can compute the fraction of heat mortality that is attributable to climate change. And this is done here and shown for many, many different countries. And for example, where's Spain? Spain is here. So this, in this study, what we found here, and here are the percentages. You cannot see it really well, but there's around 30% mortality that has taken place in Spain can be attributed to climate change. Would not have happened if climate change had not happened. And across all locations, it's actually 37% in this study period that is due to human-induced climate change. Okay, and to take this a bit further is, what we did in this global study is we did not account again for adaptation. And then I have been working also on a study again for German data where we try to also look into adaptation. And I won't go too much into detail, but I show you a bit. So again, you have your temperatures with climate change and you have it without climate change in orange. But in this case now also you account for the fact that there has been some adaptation taking place. So the risk in the earlier part of the period was higher than in the later part of the period. And then you look at these scenarios together and what you really find is that if you take account the adaptation, you actually find a decrease in the heat-related mortality over time, both for climate change and without climate change. This is just by city, it's the same thing. But if the adaptation hadn't taken place, this is this case, we would have already seen an increase in heat-related mortality. This is something that you can see here. So the adaptation has actually buffered the effect of climate change on absolute heat-related mortality in these German cities. And this is a bit the same as I showed you for the global study, where it's just the proportion of the heat-related mortality attributable to climate change. And you can see it's around 40% in this German city, and there is this strong increasing trend of this proportion that can be attributed to climate change. Okay, so then my third research question. Heat health action plans affecting and reducing heat vulnerability of the general population. So yeah, adaptation is really the elephant in the room because this is really on the past if you want to understand what happened there, but also for the future. It's very important to really understand this better. And in this study, we were really asking, are these early warning systems, are these health action plans, are they actually having an effect on heat-related mortality? And we did this for Europe. Actually, this is still in the making, so this is really current research. We have data again for many, many European cities. And here what is now interesting is that you see the year of the implementation of these heat action plans or early warning systems. So in many countries, actually after the 2003 heat wave, these action plans were implemented. So you can see here, Portugal was a bit early, I think it was in 1999, but then most of these countries implemented them in 2004, 2005. Okay, and so then we really asked the question whether we can see anything happening in these temperature mortality associations if you account for the implementation of these effects. And this is just to show that there was actually different trends and vulnerabilities in these countries. So in some regions, actually this vulnerability has decreased, like in Germany, what I showed you. So this is like Western Germany, there's like this slight decrease in the vulnerability, but in other parts of Europe, actually there was an increase in the vulnerability. So this is just as a background to this. But now for the main question, and this is very cool results I find, is that, so now I show you for these 4 regions, I show you these curves, once with the heat prevention plans in place. So as it has happened, this is the pink line. And now in these And then another result, assuming that they would not have, that this implementation would not have taken place. This is the green line, and you can see that across all of these regions, yeah, the green line is below the pink line, so this suggests that there was some decrease in vulnerability due to the implementation of these heat prevention plans. And yeah, sometimes these uncertainty ranges are overlapping, but overall there seems to be some signal that actually it's doing something on the heat-related mortality risk, these heat prevention plans. Okay, so then I think I will just, because of the time as well, I will just quickly show you a few ideas I have on future research. And yeah, one thing that we are working on is actually, again, on these heat prevention plans, really looking at the alert data. So asking, for example, for Spain, it would be like whether these heat alerts you get from AEMET, so aviso de ola de calor, whether this actually has an effect on reducing heat-related mortality. And we are trying to do this for all of Europe, and we are just currently trying to collect the data. So that's something that we are working on. And I will skip this. And then I'm also involved in a big consortium which is funded by this one, by Wellcome Trust, which is like a foundation funding health research. Where we will do more attribution work. So also, and the nice thing is this will also look into hospital admissions, so moving beyond mortality, but looking at other health indicators, very specific also health indicators, which I think will be very interesting. And yeah, I put a little question mark. I hope that there will be a postdoc that can move here, but let's see. And then this is actually my last slide. And because, of course, I have this ecology background. Now I'm doing environmental epidemiology, and I ended up here. And I found it funny because today is actually a holiday in Germany. It's the reunification day, the 3rd of October. So I thought about this reunification, and I thought, okay, so there's environmental epidemiology and there's freshwater ecology. And let's see what comes out of merging them. And so, of course, there is ideas on waterborne diseases, but I have some ideas on, I don't know, parasites, waterborne parasites that one could work on, or maybe also something on biodiversity and health. I would be very much interested in exploring this without having any concrete ideas, but yeah, who knows? And then there's just some question marks for maybe some other very innovative ideas. Okay, and with this, I thank you for your attention. And of course, I thank all of my colleagues, students, and important collaborators over the last years. And I also put this, for those of you who were in the seminar last week, I have been involved in some scientist rebellion actions. And so, yeah, feel free to come to my room and contact me on science, but also if you're interested in this stuff.
Oh, sorry. Thank you, Veronika. Just wanted to do a little reminder before we start questions, just to encourage as diverse of people to ask questions as possible, which I'm looking at PhD students and stuff as well, just so we get a, not that it's bad that we have, but it does tend to be the same sort of career stage people asking questions, so just to encourage everyone. Okay. Anyone want to start? I've added a lot of intensity to that. I do appreciate that. But I could get the ball rolling if you like. So you've taught, fantastic talk, by the way. You talked a lot about temperature change, and especially from the figure on the one that it's Europe-wide excess mortality, temperature-related excess mortality for lots of different cities where the UK was doing better.
Yeah.
That got me thinking about precipitation extremes as well, which obviously also that one. Yeah. How does precipitation extremes fit into this work? Is that something you've worked on? And
yeah. Thanks a lot for the question. Yeah, actually, I have been involved in another study where we looked at precipitation extremes on mortality, all-cause mortality, but also respiratory and cardiovascular mortality. And actually, you find a signal of extreme precipitation on especially respiratory mortality. Mechanistically, I cannot really tell you, but there seems to be, for example, also like a signal on this. Yeah. Beyond, of course, extreme precipitation leading to inundations and
or like flood, just like infrastructure as well. Yeah. Interesting. Cool.
Thank you. That was really interesting. And I have a question. Maybe the answer was in one of your slides. You had the actual cause of death, the cumulative effect on people's health of temperature increase, or how much of it is a more immediate response?
Yeah. So the way, you normally what you see is a sample, and then 2 days later you see these spikes in mortality, as I showed you for the severe case. And most of it is actually acute. So most of the deaths are actually, for example, people with for example, they have heart problems anyways, or they have chronic respiratory diseases. And then due to temperature, this is just getting so much worse that then people eventually die. So this is really the main mechanism is this. Because it's just, as we know, heat is a stress on the body. Of course, you have to move your blood to the skin. You have changes in your fluid compositions. You have strain on your heart and your kidneys. And so then for people who already are sick, then it's more likely that they die. So this is most of it.
Yeah, thank you very much. Yeah, okay, thank you very much. I have one question, is when you show the model, there was a term that were confounding effects, but you didn't mention which ones you consider more important.
Yeah.
Which
Yeah. So
besides differences in seasons.
Yeah. So actually, for example, for cold-related mortality, most of the time people try to control because for infectious diseases. So where we have data on this, of course, that's super important because part of the seasonal pattern is due to influenza epidemics, for example, or some other viral epidemics. But if we do look at this for the whole temperature mortality, normally it's just things like day of the week or some very basic confounders. Yeah.
And in terms of future work, I think that it would be very interesting if you could focus on water shortage, because this would be, I think, the main problematic issue in many towns in Spain and in Southern Europe in general. We think a lot on temperature, but to have water that you can drink at home or not, it's a big ississue already.
Actually,
especially
maybe
in
it's
summer.
a cool idea because wasn't there these water shortages in the 1990s already here in Sevilla? So maybe there's data on this, and one could try to see whether you can find any effect of these type of shutting off water for some time during the day, and whether you can see anything in the health data.
Yeah, and not only water shortage, but not having drinkable water at home.
Yeah.
Because this is going on in towns in summer, and even all year round. And this is a recent phenomena from the last 15 years, 10 years. I mean, I know the area in North Spain, in Catalonia, but this is...
It's actually a very nice idea. Thanks a lot. But because it was feasible. It would be feasible to look at this.
Thanks, Veronika. That was super interesting. So I was wondering, because of my perspective also, whether you mentioned a socio-demographic variable you have been studying, which is age. And I was wondering about other social factors, namely gender, class. We actually did with a very small project a case study in Seville and comparing the neighborhoods, so the socio-demographic conditions and the statistics on deaths over extreme heat events. And actually there was a strong correlation. So I wonder whether the data is available at the global scale to test this kind of hypothesis.
Yeah. So yeah, on a global scale, it's a bit difficult because, you know, for example, for Germany, we cannot even put into this collaborative research network, we cannot put mortality by sex, by age. It's only the death count, so it's only the number of deaths per day. But there's a lot of studies on this. And for example, on the question of gender, there's very nice studies showing, for example, that elder women are more susceptible than elder men, which, yeah, it's just an interesting finding. But for example, maybe you've heard about this. There was this there was this European Court of Human Rights, and there was actually this court case brought forward by Swiss women, and they actually based all of the arguments on this finding that women are heat waves than men, because there's quite good scientific evidence on this. Yeah, and then on the socioeconomic factors, I haven't been involved in any studies, but there's also very nice studies, for example, from Madrid, that also have data on social deprivation across different neighborhoods, and they actually find what you just said, that in more socially deprived neighborhoods, you have stronger heat-related mortality risks than in richer neighborhoods. Yeah.
Thanks.
If nobody's asking, have you thought to expand your epidemiological studies to animal mortality, like a wildlife animal? Maybe you have data on that, or?
Yeah, I haven't done so, but as I said, like I'm new to this institute, so if anyone has mortality series from any wildlife, it would be very cool to see whether you can use these type of approaches.
I think maybe with rabbits you can find something.
Yeah, I think it would be very nice, because I think these methods are very well developed, and it could be very nice to just see whether what can be done. So feel free to approach me, and I send you my R code, and you can.
The only thing I would say that we struggle with is the amount of data by far. The time series, humans are exceptional.
Yeah, I think I would agree with that too. I think there's no way you're going to get such good data from animals, plus all the detection issues. But that's I mean, technically it would be a great idea to do that. I agree with Irene. Anyway, thank you also for the talk from my side. My question is also a bit, now that you have the slide. I know that, for instance, in ecological study, these types of and maybe they're more complicated than it looks like, but these types of relatively simple regression models have now come a bit under critique, and people that try to do like proper path analysis. So looking at, like this, what they call the DAG, the graphs of trying to identify the proper drivers and how they interact, and is this something you guys are also doing, or, like to look at the mechanisms actually, some causes? To get causes from the data.
So this is really the type of methods people are using all across, but of course there's always this issue of confounding. So, for example, on these, for myself, just like my intuition is on the heat-related mortality, this works quite well, but on the cold-related mortality, they're much more confounders, and I think for sometimes these seasonal controls are not good enough for them. So, but I don't know of any study that tried to really be, more process-based or more mechanistic and trying to figure it out. But I see the point. I see the issue. Yeah.
Thank you.
Well, thank you very much, and welcome to EBD, I guess. So I think it's a very interesting research line for our institute, so that's quite cool. So I understand that at some point the outcome of your research have to be translated into political actions for the political class. So I guess that the politicians are waiting for indications to take actions. So in your opinion, which would be these actions? So because I'm quite confused about, perhaps it's better to invest public money into teaching population how to behave in a heat wave, Or perhaps, what we have to do is to invest funding into rehab works in households, because I think that our cities are for past climates, but our cities are not ready for the future. And that's a very important economic and social change. So I bet that you guys are working on this kind of direction, but I'd like to know your opinion about the best actions to take from the political class.
Yeah, so, regarding these adaptation options, so there is a bit of thinking about how to rank these. For example, you could exactly ask this question, is it better to put air conditioning in all the houses, or is it better to put a lot of trees in all of the streets, or put like these water sprinklers around? And so there is a bit of work in trying to first see whether there's an effect really on mortality. And then really also to kind of, start comparing this. But this is there's nothing really yet, I think, I would say. And for example, for the work that my last key research question, we were actually surprised that there's very quantitative evidence of the effectiveness of these heat wave plans or early warning systems. But the good thing is that there's much more research now also from the social science, where they really try to see, okay, if there's somebody gets a heat warning, do they actually change their behavior? But I think people are trying to get better, but there's no real conclusion yet. And my own gut feeling, if you ask for this, without any scientific evidence, is especially Northern Europe needs to invest heavily in air conditioning and climatization, because we know we have evidence that in climatized homes, heat-related mortality risks are lower, but there's still Germany, all of Spain has air conditioning, but up north, there's very little air conditioning penetration. And I think my gut feeling is this is something that can save a lot of lives. And so people have to, although it's, energy-wise, it's a nightmare, but you have to think about how to do that. Thanks.
Thanks for the nice talk. I'm wondering, concerning your first research question, the one about the future projections, there's this idea that it's not the mean increase in temperature that is causing death, right? It's the extreme events, like mentioned here already. But I was wondering if these projections into the future take into account this increase in the frequency of these extreme events, and if that's correlated with increase also in the mean temperature. So
very nice question.
It's really curiosity. I don't know if it's correlated, the increase in the frequency with the mean.
So, as you say, I think there's clear evidence that we know, the thermodynamic component of the global mean warming. We know, so as you say, the mean is increasing. But then there is these kind of, indications that through these, for example, changes in the jet stream, in these changes in the atmospheric circulation patterns, you also get, for example, more heat extremes in Europe. But these dynamic components of global warming, they're not included yet in the global climate models. So all of this, like this kind of stalled jet stream, and then therefore you have these extremes, it's just not represented because I think it's still not quite well understood. So this is why we might underestimate actually this heat-related mortality in many of these studies. Yeah.
Anyone else? Any other questions? There's nothing online, no? No. Okay, I think with that, thank you again, Veronika, for a fantastic talk. I think it's just from my personal perspective, it's quite similar to the work I do. So it's nice to have like a human example for something that I'm doing. So it's like, I think there's a lot of potential collaboration, and
cool.
Welcome. Thank you very much.